I think we should begin now. So let me just share the screen. Right. So I hope the screen is audible. Oh, I'm audible and the screen is visible. So I just want one confirmation. If anybody can just tell me. I hope.
Yes, sir.
Okay. Thank you. Yeah. So today, we have done so far how a computer would store integer numbers, how a computer would store floating point numbers. Now we come back to errors, because that's probably the most important part of this entire unit. So we'll talk a little bit about how the error propagates. And if we look at the various operations that a computer actually performs, then it's just basically addition, right? I mean, if you look at subtraction, that's also, adding two numbers. If you're multiplying something, that's also repeated addition. If you're dividing something, well, you can also write it as a product form. So actually, if you look at it, all these operations, and there are just these four operations that a computer generally performs. I'm not talking about the logical operations, but the arithmetic operations. So you have the addition, you have the subtraction, you have multiplication, and you have division. So we look into these these arithmetic operations, and we'll see how the error will propagate when we're adding two quantities or subtracting two quantities. It's something that you've already done in class, maybe 11th or 12th, but I think it's significant that we visit it again just for clarity, and maybe it will be a quick revision. And then we'll talk about a couple of other things. Let's start with error propagation. So what I mean by error propagation, I'm making somebody the co-host, and I would just request you to probably enter. Tarun, would you be okay being the co-host?
Yes, sir.
Just a second. Can I see? No, I see Abhit first, so I think I'll just make Abhit the co-host. Tarun will be relieved of that duty. Abhit, is that okay with you? Yeah. Okay. Thank you, both of you. Okay, let's start. So we are looking at error propagation. So there are four arithmetic operations. And we are going to look into how the error propagates in this. So one is, addition. Second is subtraction. Third is multiplication. And fourth is division, or sometimes it's also denoted by a multiplication. So we'll see. So let's see. Suppose we have two quantities. Let the quantities be x and y. Let xa be the approximate value. Two quantities, you could consider this as the true value. And y a be the approximate value is equal to x. This is approximately equal to y. Okay, so x minus xa, let us call this as error ax. Okay, Well, this is the absolute error basically. Okay, and then y minus y be called as absolute error in y. Then we also can define x minus xa divided by x, and let's call it the relative error in x, so subscript rx, and similarly let's say y minus y over y is relative error. Okay, so let me just I think this is understandable. So these are like absolute errors. And these are relative errors. Okay. All right. So let's let's look at um, first case of addition. So when you have x plus y, so if you see from the point of view of if you see this equations by absolute errors, then I can just say that it is xa plus eax and plus ya plus ea. Yeah. So I can probably write something like this. I can say x plus y minus xa plus ya is equal to eax plus eay. Now, since we are only interested in the magnitude of the errors and not really the amplitude, so if we take the magnitude on both sides, so this is x plus y minus xa plus ya, and that is going to be magnitude of eax plus eay, and you know that this is going to be less than equal to magnitude of error in x. So basically you can see that when you're adding two numbers, then you're basically going to be adding their approximate values, and then if you see that there would be some error that will creep in uh, because both of the quantities x and y have errors, and the ultimate finding is that it will just be the sum of error of x plus sum of error of y. Now if this keeps on growing, if you're doing a lot of additions and this keeps on growing, then we have an issue, right? Because then your result is going to diverge as we have discussed. So this is the absolute error or error propagation which the addition follows. So one can say that the absolute error in using xa plus ya as an approximation to x plus y is less than equal to the sum of absolute errors incurred using xa as the approximation of x and ya as the approximation of y. So I'm not going to write it, I think it's evident, but I just wanted to make a point. All right. So let's look at the second case of subtraction. So subtraction will follow similarly. So you'll have x minus y is xa minus ya plus eax minus eay. So if I take the magnitude on both sides, xa minus ya, it will be just the magnitude of ax. And this is also less than equal to eax plus. We're generally interested in how the individual errors will add up. So this is again an inequality, and It means that when you're adding or you're subtracting two numbers, the error is more or less in the range of EAX and CA. So this is for subtraction. If you look at multiplication, you're multiplying quantities straight away. So basically, if suppose you multiply the approximate value with the y approximate value, so this is going to be x. What was it? Put in a formula for it, right? Sorry, we basically, yeah. So xa is going to be x minus eax y minus ay. Right? So if I take x and y out, I'm left with eax over x 1 minus ay over y. So xa over ya is equal to xy, and eax over x is simply erx, right? Because eax is x minus xa divided by x will give you the relative error. So this is e minus rx times e minus ry. So so what you can do is you can probably write it like this. So this is going to be 1 minus ry minus erx plus erx ery. So let's take them on the other sides. So you could say that erx plus ery minus erx plus ery.
Excuse me, sir.
Yeah.
So wouldn't the entire thing in the bracket be the relative error?
No, it would not. This entire thing in the bracket. This is what you're saying.
Yes, sir. Like 2-3 lines above.
2-3 lines above means.
Equals xy bracket 1 minus eax by x bracket close.
Yeah. So this would not be the entire error, because the entire error would be entire relative error would be this quantity. So I was deriving that quantity actually. This would be the entire. This would be the relative error in multiplication, no? Because you're multiplying something, so the exact quantity should be x into y. The approximate value would be xa into y. So then this would be the relative error. So I'm coming to that expression. You will see that we will come to that only. So xa over ya over xy. So if you take mod on both sides, now this is the relative error in multiplication. I hope now it's clear. Right, but now I mean you can just see that considering that the relative error in x is of a very small magnitude, and so is the relative error in y. So this product is going to be even more smaller. Like for example, if this is 10 to the power minus 4 erx, and this is let's say 10 to the power minus 3, that means the product is going to be 10 to the power minus 7, which is going to be like a very small quantity compared to 10 to the power minus 4 or 10 to the power minus 3, even though they themselves are very small. So for all practical purposes, generally people neglect this. So if they neglect it, then the relative error is simply going to be the relative error would be, if suppose you neglect, if erx ery is neglected, and I've just told you why it will be neglected, because it's much smaller than both erx and ery. So one can say that the relative error in the product, which is this quantity, is going to be the relative error of x plus relative error of y, which would then be simply less than relative error in x plus relative error. In case you can't do it, then you just keep it this way, and then whatever value comes here. This is what it is. Okay. So I hope that now it's clear that initially when you were mistaking this to be the relative error. Actually, if you look at just the product of these two terms, then that is simply the ratio of xa y over xy. It's not the relative error, because relative error will be defined by this quantity here. In any quantity, this would be the relative, because we're doing a multiplication. So the quantity is basically z. So we could say that z is xy, and za is basically xay, and then relative error will be z minus za over z. So this is basically it. I hope that is now clear. Okay. So moving ahead, we'll see how the error would propagate when you are actually dividing quantities. So let's say change the division. So when you're dividing quantities, you have xa over ya. So so this would be basically x minus erx divided by y minus ery, sorry, ay. Okay. So now if I take x common in the numerator and y common in the denominator, so I get x, y like this, and here I get relative error in x divided by 1 minus relative error in y. Okay. So let me also, just because I don't want to write too many divisions, so let me just call x by y as alpha and xa over ya as alpha a, and we are basically trying to find what is mod of alpha minus alpha a divided by alpha. That is what we are trying to find out. So let me just write it as alpha a is equal to alpha. This becomes 1 minus e to the e minus rx into 1 minus e to the power e minus ry to the power minus 1. Now we know from binomial expansion, I'm sure that you know that when this quantity here is, so the rule is this. So if you remember, this was e to the power mod, and if mod x is much less than 1 or less than 1, then this simply becomes equal to 1 plus nx. And of course you can increase the power of x and it will go as a power series, but for all practical purposes, because x is small, so x will be even smaller, you can neglect it. So this is the small binomial expansion when mod of x is less than 1. So I can write alpha a over alpha is 1 minus erx 1 plus ery. So basically ending up with a similar kind of an expression, ry minus erx minus erx minus ery. Okay. So now if we take it on the other side, we get erx minus ery minus erx minus ery is equal to alpha minus alpha a over alpha. If you take more on both sides, so you get. So again, you're getting an expression which is quite similar to subtraction, where if you neglect erx multiplied by ery, and counter being very small compared to erx and ery individually, then I can say that the relative error alpha minus alpha is less than. So this is how the error will propagate. So you should remember that when you're doing additions, and we're basically doing additions, this is how the error will propagate. And if you do multiplication, it's a relative errors that get added. And relative error seems to be a much better um, measure of how your error is propagating, because it gives you the error with respect to what the true value is and what you would want it to be. So that gives you a better indication. Like if suppose your true value is 0.1 and your error is coming out to be 0.08, then that means that it's a huge error. But if you have a value x to be 1000 and your absolute error is coming out to be 0.08, then the relative error is very small, right? So relative error will give you a better indication of how close you are to the true value, or how close you are when you have two adjacent values that needs to be matched to come out of the iterated loop. Because it's not always that the true value will be given to you. In that case, you have to compare the value which is at the ith iteration with the value which is at the I minus 1th iteration. So the relative error will be xi minus x subscript I minus 1 divided by x subscript I. Right? So that's how you proceed. So you could probably think of some sort of numericals here, but ultimately you can try these numericals. I think there is no need to really go too much into it. Now, there is just a couple of things I want to mention. So first of all, if you remember, there are two laws that are very popular, so to speak, when we do arithmetics. One is an associative law. Right? So associative law says that A plus B plus C is same as A plus B plus C. Okay? So this is an associative law. And then the second is a distributive law. And this law is nothing but A into, this is equal to AB plus C. Okay? So generally, so these laws are valid when you have integers, but when you have floating point numbers which are truncated and rounded off and so on and so forth, then it's quite likely that these may not always be valid. So this is an important statement I'm making, and you can take some examples and prove it yourself. But I'm just making this statement because I'm just covering fine bits, because you're coming to an end of this topic. I want to just point out some important things. Maybe I'll give you some practice problems in which this will come. But the thing is that what I want to say is that for normalized floating point represented numbers, so I'll write this. This is an important thing. Mark it like this. So for normalized floating point representation, the above mentioned laws may not hold. And they may not hold. They may hold, they may not hold. But they will not always hold. That is what I basically want to say. So this is an important thing. And in fact, if you look at it, let me just probably point out some of the pitfalls of floating point representation. So let me just point that out. And this would probably be the topic which would be called as the pitfalls of floating point representation, or some issues that you may have in floating point representation. So let me just mention pitfalls of floating point representation. So I'll just probably write these pitfalls, and when we do some, I think probably, uh, I think after today's class, we will finish this unit by the end of this week. So we have 2 more classes. I think today it's already 9:30. I'll cover some theoretical parts today, maybe a little bit tomorrow, and then for the remaining 1.5 classes, we'll be doing some numericals. So when we do those numericals, I think we'll revisit these pitfalls, and I will show, or I would not show. We'll do numericals in which it will become very evident that these laws do not hold when we talk about floating point. Okay, so I'm just pointing out things. They will become more evident when we do and we try to prove them by doing some numericals. Okay, so pitfalls of floating point representation. So I'm right now. I'm just simply writing it, and then we will revisit them through numericals. Okay. So the first thing is that something like this may not hold. For example, often we say that, like even when we were doing that error propagation, I said that, multiplication is nothing but repetitive addition. But with floating point representations, that may not be true. Like what I mean to say is that it may be that, let's say, 3x is not equal to x plus x plus x when you do floating point representations. Generally, arithmetic says that they should be equal. But when you do floating point, then they may not be equal. Or for example, 4x may not be equal to x plus x plus x plus x. What I mean to say is that if suppose I give you some x and you're performing 4x and you're getting some result, it would be different from the result that you'll get if you add the same x 4 times. So you take these two, you add them, then you take the sum, and then you add these, and then you take the sum and you add these. You will get something which will not be equal to 4 times. That is what I mean to say. So we will do that as an example once we are doing numericals, but this is something which is important. Okay. So then I've just told you that the associative law and the distributive law may not hold. So associative and distributive laws may not. Okay. And then there is another thing, that while performing floating point, arithmetic, the equalities of equations may not hold. What do I mean by that? I mean something as follows. Suppose I have an equation which is x squared minus 2x minus 2, right? And if I equate it to 0, then if I solve this equation, I will get roots as -1 plus minus square root of 3. Right? By that discriminant rule that you know how to solve quadratic equations, you will come to know that this is the solution. There are 2 solutions. This is it. Now, this is something which is written like this. If I put this x in this equation, I'm guaranteed that it will be equal to 0. So equality is satisfied. But right now I'm writing this not as a floating point number. I'm writing it just like I write when I do in the decimal format. I'm writing it the way we have been trained so far. But this is not how the computer sees it. But if suppose the computer sees this and so the two roots are basically, so the two roots are x1 is -1 plus root 3, and the other root is x2 is -1 minus root 3, right? So if you write it in floating point representation, we come to that when we do numericals. In the normalized form, this would be written as 0.732 0 if I take only 4 decimals, e is 0. Okay? E means exponent. So this is how we write it. And then the other number you write as minus 2732E1. Okay, so this is how you write this one. And if now with any one of these, if you try to solve this, so if you try to do this now, which is x1 square minus 2x1 minus 2, and you evaluate this quantity, and you will see that this quantity will not be equal to 0. If you take x2 square minus 2x2 minus 2 and you evaluate this quantity, you will see it will not be equal to 0. You can check this later. So we'll check this later. But I'm just making a statement here that when we do floating point arithmetic, the equations where we know that there is an equality, well, there will not be an equality, and this will be. Okay. So these are some pitfalls of floating point representation that I think you people should know. All right. So I think we are almost coming to an end of these things, but so I think let me just remember if there is anything that I'm missing. I think there isn't much that I'm missing. We can just probably start off with some numericals even today. Okay. So let's do this. Let's do some numericals today. So please take your calculators out. We have about 20 minutes. We'll do some numericals. Okay, so let's say that the solution to a problem is given to you. So there is a solution to a problem. Solution to the problem is given, and it is 3.436. What is it? It is known that the absolute error in this quantity is, let's say, 10 to the power of minus 2, for example, or this could be written as 0.01. Okay. The question is, what is the limit in which the exact value must lie? So the question is, what is the limit in which the exact so this is the question. Okay. So you are given x minus xa is somewhere greater than less than equal to the error, which is x, which is x. So you have mod of x minus 3.436. Just a second. हेलो, हाँ, गुड मॉर्निंग दीपक जी, कैसे? दीपक जी मैं क्लास ले रहा हूँ, मैं करता हूँ थोड़ी देर में आपको कॉल. ओके. Yeah, so this would be something like this, 0.01, right? So what does this mean? If you have mod of something which is less than equal to this, so that means that you have 0.01 minus x minus 3.436 1, right? So you write it, and now this magnitude sign corresponds to a normal bracket. So that means now your x will lie between 2.436 minus 0.01 and x will be equal to 2.436. So we can evaluate this. This would come out to be 0.01 minus 12, so this would be for 426 x, and this would be 2.446. So this is the range in which your exact value will lie. You don't know what it is, but you know the range in which it will lie if the error is this. So if the error is more, the range will be bigger, and that much more will be the uncertainty, right? So this is what it is. Okay. Now let's do another problem. Let's look at a problem where we take some sort of error also, and we give it a particular name. I think probably I would want you people to solve it and tell me. Suppose I say that let x be 0.00458 529. Okay, so I think the first thing that I should probably tell you when we do these problems is that how we would write normalized form. So we did something called as a scientific form. I told you at that point of time in the last class that sometimes people call it a normalized form, but I would like to differentiate between the two. Scientific form is 1 plus mantissa times 2 to the power something if it's a binary number, and 10 to the power something if it's a decimal number. But normalized form for any decimal number, I will write as follows. So let me just give you that normalized form first. So normalized form would be written as 0, d1, d2, d3, 2d, and so on into 10 to the power of n, okay? Where n is whatever comes when you write it in this form. So these are all these values d1, d2, d3, d4, dn. So d1 has to be non-zero. The others could be zeros, but d1 has to be. And d1 cannot be. So this is called as normalized floating point. किसी का mic खुला हुआ है, so just close that mic. And just maybe we'll take a break of 2 minutes. I just have something. हाँ बताइए. हाँ बंद कर उसको बंद कर दीजिए. Thank you. Right. Sorry. So this is the normalized form. So we'll work with this form when we're doing numericals, floating point. So this is the normalized form of the floating point. So if this is the number given to you, let's say, and I'm asking you, find. So this is an offshoot. And this is important. So the question is find the absolute error when x is truncated, when x is truncated to 3 decimal places. 3 decimal places. Okay, so this is it. So the first thing that you do is that you're given an x which is 0.00458529, right? So you will write it in normalized form first. So normalized form will be, so these two digits d1, so this is a 0, this is a 0, so obviously d1 is a 0 and d2 is a 0, but we know that d1 cannot be 0. So what we'll do is we'll take this and we'll come here and then we'll come here and we write it like this. So we write it as 0.458529 and this becomes into 10 to the power of minus 2. This is also written as, one can also write it as 0.458529 e minus 2, right? So that is e. It's just the exponent to the power of 10. Okay, so this is the number in the normalized form. Now I'm telling you that we will truncate it to 3 decimal digits. Remember, I'm saying we will truncate it to 3 decimal digits. So the 3 decimal digits are these digits here, right? So that means the truncated form is going to be 0.458 into 10 to the minus 2. So if you have to find out the absolute error, so the absolute error is going to be 0.45859 minus 0.458 into 10 to the power of minus 2. My phone आ रहा है, प्लीज उठा लीजिए. Just a second. So this is the absolute error, and in this case it's a positive quantity, so I'm not taking a mod, but in practice this would be actually a mod. So if you look at it, then this would be 0. What will be, so you get 0.00529 into 10 to the power of minus 2. So this is the absolute error. So this is the absolute error when you're truncating it. So if I give you another numerical and I say let's round it off to 3 decimal places. So let's look at that also. So let's look at this example. I think we'll just end it here today and we'll not go any further. So now what is the absolute error? So the question is, for the same problem, absolute error if we round off at 3 decimals. Please remember the word is round off, not truncate. So the number we had in the normalized form was 0.458529 into 10 to the power of minus 2. So now when we are rounding it off to 3 decimals, so these are the 3 decimals, but while rounding off, if you remember, we look at this value here as well. So if it is greater than 5 or equal to 5, we just add 1 to the preceding value, otherwise we let it be. So round off value, the round off value, किसी का mic खुला हुआ है, इसको बंद कर दीजिए.
So if it is 5, then we increase the previous digits by 1, only if it is not even.
Only when it is not even, you say. I don't know whether it's like that, but I don't know. I mean, let's say that we can round. I don't know. I mean, I don't want to argue on this rule because my understanding of this is that if it is 5 or greater than 5, then we just increase it by 1. But let's just go by that only, because if you don't go by that, then the round off error will be the same as the truncated error. But I want to show that the truncation error and round-off error may be different as well. So that is what I want to stress here. So okay, so just just check once. That's my understanding of how round-off error goes. But you can just check once and let me know by next class if what I am saying is correct, or what if you are saying is correct, or if you are saying something, just give me the source and I will probably go through it. Okay. So you can just post it on the Google Classroom, the link in which you just read this rule. Just I would want to see. Okay. But let's say that what I am saying is how we'll go. So then this would be 0.59 into 10 to the power of -2. So if you now calculate the error between the two quantities, so that error value will now be actually negative because the approximated value is now greater. So you'll have something like minus 0.000 ये हो जाएगा 4.7 something into 10 to the power of -2. So if you take the absolute thing, so then this minus sign will go. So you can see that these two values are different. What I really want to stress is that the truncation error and the round-off error may not be the same. Okay? That is what it is, and you can cite this rule that you just mentioned in the Google Classroom. I'll have to look at it, and then if it is true, then we'll just follow that as well. So what you're saying is that if this number is 5 or greater than 5, then the preceding number changes only if that digit is odd, but it doesn't change if the digit is even. Is that what you're saying? No response.
Yes, sir. The rule like that.
It's like that. एक बार जरा दिखा देना मुझे, because I mean I may be wrong, but that's what I have gone through all these years. Anyways, but I hope that the lesson to take home is very clear, is that when you're truncating something and when you're rounding off something, you may end up with different errors. That is basically the lesson that I wanted you to register in your memory. Okay. All right, then I think we'll end the class here today. In the next class, we'll start with some more numericals, and I think we should be able to finish it by next class. So this unit will be over, and then we'll move to linear equations. Okay, we'll start first do linear equations, and then we'll go to numerical equations. Okay, thank you. Good day. Yeah. Is there anybody who has an issue? Okay. All right then. Bye.